for NEET is now available on the Google Play Store. Try it out for free.
Today, we will be looking at atoms. Um, so, to understand atoms, this is actually a very not that difficult part of your material, and particularly for students who take exams like good set, or other board exams, etc. This is the kind of material that you should cash in. Okay? You should get all the marks in in these kind of chapters. So to quickly go over a good set material, you can see that basically electrostatics. There are two chapters of electrostatics, one chapter of um, you know current electricity, and then magnetism, and then electromagnetic induction, then alternating current. We've gone through several of these. Then there are three chapters which deal with waves. Okay, and that you have three chapters or four chapters that deal with um, modern with modern physics and semiconductors, and finally one chapter with electronics, which is basically and we have all the lectures covered. So with respect to atomic models, the first idea of like in those days people didn't know what was inside the atom, and rightfully so, because you cannot see. When you see homogeneous material, right? So you cannot see what is there, and so then they were trying to understand. They had this postulate of atoms because it came from chemistry, right? The nucleus, as we know it today, we understand nucleus and all that, but in those days they didn't understand that at all. Okay, they only knew, they could only guess that an atom consists of positive and negative charges, and that as a whole, so this was the first theory made by Thomson. Okay, J.J. Thomson. J.J. Thomson, he first said that it is like a pie, you know, and that I hope you can see my screen, right? And that um, when you look at um, it could his model, he said that there are inside that pie there are positive and negative charges embedded in it. It, of course, could not explain all the spectral series from hydrogen and other atoms. It could not explain, the kind of scattering that was happening with alpha particles, and we'll go over that. Okay, the scattering experiment, etc. Okay, so this model was called plum pudding model. Okay, then the next model that challenged this model was made by Rutherford. Okay, Rutherford is also not the final model. Okay, the Rutherford model relies on a planetary system, right? You look around, and by this time the heliocentric theory of the planetary system was well established. The sun was at the center and large, and then the planets were at a significant distance from the sun and revolving around it. And so that was the model that Rutherford brought up. Okay, and so he produced a lot of statistics to explain his model. So there is the plum pudding model of Thomson, where you have a pudding, plum pudding, and then you have embedded in the plum pudding plus and minus. And this was wrong for because of the spectral series and the angle deflection. The why does and so Rutherford, what he said was, on the basis of this alpha particle, like some alpha particles just go right through. Okay, but there'll be a few that would deviate significantly. So what did that tell you, right? So that told you that there were certain there was a certain concentration at a very small part of all the positive charge. Okay? So if you have a accelerating alpha particle, and then it kind of deviated significantly, it means that it went really close, and then by looking at the track, you can then postulate the concentration of it. So there must have been some that really had large scattering, that is, they would go like this and then they would get repelled and get pushed out like that, or go like this, repelled and pushed up. So what caused that? Basically, it almost collided with the nucleus, or it came so close and then it deflected and went that way, right? And so using that, based on how fast the incoming alpha particle was, remember, an alpha particle has positive charge, and that was very well understood. The level of positive charge in an alpha particle was very well understood. Okay. So it came like this and then it deviated. By this time, they had found all these. Um, uh, they knew there was a positively charged element, and then there was a positively charged particle, there was a negatively charged particle. That was very well. Now, so he came up with this basic model. The entire positive charge and almost the entire mass of the atom rested and is concentrated at its center in a very tiny region it's of the order of 10 to the power of minus 15, called the nucleus. Okay, so remember that what is 10 to the power minus 15? It is smaller than this thing called the angstrom. The angstrom is 10 to the power of minus 10. So this is 10 to the power of minus 15. So it's so small. So if you look at such a large space, it's a small pinhead on that large space. Okay, so the negatively charged electrons revolve around the nucleus. The total positive charge nucleus is equal to the total negative charge of the electron. Therefore, atom is overall neutral. All right. So now let's look at this Thompson model. Okay. So Thompson model, what it does is you have the you have everything will be going straight, right? The Thompson model, it's like a pie, and with a pie with a lot of things, a lot of embedded particles, right? Thompson model had been correct, you would not have been able to explain this deviation, because it's all like uniformly spread out, right? There wouldn't be this level of scattering, right? And so in the experiment, Geiger Marsden, right, um, observed that a small fraction of the alpha particles experienced strong deviation. Okay, so alpha particles are emitted by essentially by radioactive elements, which, and then they are attracted. You have this on this side, you have a uh, uh, negative, seriously negative charge, so you have a positive charge which is accelerated towards that negative charge, so it comes here and then it hits a thin gold foil. What they found was some of them would deviate like extremely large deviations. So that large deviation, the largest deviations, told you the corresponding nucleus. So he said that all the positive charges centered in a very small concentrated space called the nucleus. So if there's anything, you can say that he invented the nucleus. This idea of a nucleus and the negatively charged electrons revolving around. Okay, the total positively charged nucleus is equal to the total positively charged electron. So he had four postulates. Okay, the first and second postulate, right, in the Rutherford model, right, the entire positive charge and almost the entire mass of the atom is concentrated in the nucleus. Okay, the electrons form a cloud. Okay, here the third point was the total positive charge is equal to the total negative charge. Okay, and finally, the centripetal force felt by electrons for revolution is provided by electrostatic attraction between the electrons and the nucleus. So they how do they sit there? They experience a electrostatic attraction, and therefore they revolve in an orbit, right? We all know the sun and the planets model. Sun is at the center, the planets revolve around the sun, and what holds the force that holds the planets in place is gravity, right? Here, the force that holds the electrons in place is electrostatic force, right? So the electrostatic force keeps the electrons revolving. Okay, and so the distance of closest approach, he is r naught is given by 1 by 4 pi epsilon naught z e square by ek, where ek is the kinetic energy of the particle, the cc particle. Okay, so um, the kinetic energy of the particle, right, equals what? Half mv square, right? Half mv square is 1 by 4 pi epsilon naught z e square by r, right? What is the corresponding energy is 1 by 4 pi epsilon naught z e square by r, right? And that is z e square by r square will give you half mv square, right? And so from that, if you look at the so half mv square, right? 1 by 4 pi epsilon naught z e square by r equals the equals the so that what does that give you, right? So 1 by 4 pi epsilon naught z e square by r square will give you the force, right? That is equal to and from that, the force essentially produces that is m dv by dt, right? And therefore if you do mv mv dv, right? If you write dv by dt as dv by dr times dr by dt, right? So that will then become mv dv, right? And then you can take the dr to the other side. So then you integrate both sides. So when you integrate both sides, you end up with this equation. On the left hand side, you'll end up with half mv square, right? Mv dv, if you integrate, what will you get? Half mv square, right? And on the right hand side, what do you end up with? 1 by 4 pi epsilon naught z square, z e square dr by r square. When you integrate dr by r square, what do you end up with? dr by r square, you will end up with r to the power of minus 1 by minus 1, right? And therefore, you will end up with 1 by r, okay? And so as a result, on the left hand side, you end up with half mv square. So the 2 also crosses, so that is this 2. Therefore, you have this r naught equals 1 by 4 pi epsilon naught 2 ze square by ek. Ek is what? Half mv square. Okay, so you cross multiply the r, right? When you integrate d by r square, you end up with d by 1 by r, right? So you end up with 1 r naught equals 1 by 4 pi epsilon naught 2 ze square by ek. Okay, so from the force equation, m dv by dt equals 1 by 4 pi epsilon naught ze square by r square. We then derived this equation for r. Okay, so the perpendicular distance of the velocity vector of the alpha particle from the central line of the nucleus, the particle is far away from the nucleus, is called the impact parameter. Okay, so the impact parameter is given by that. Now, Rutherford's scattering formula, so where z is equal to the atomic number of the nucleus, ek is the kinetic energy, right? And theta is the angle of scattering. So he came up with this equation for that derives this b. Okay, b is called the impact parameter. Okay, impact parameter is given by this. Okay, so this defines the angle, right? And the angle of scattering. Okay, so um, so he then derived this idea for the scattering formula, which is kind of like a statistical model for for the the number of C particles. And guess what? He was right, because with respect to the nucleus, he had got it perfectly on the dot. It was concentrated. It occupied a very small space, and then that's what explained the deviations. And so the size of that nucleus he was able to estimate using these equations. So it is an inverse measurement, right? Based on the number of alpha particles coming in and the number that deviate and the number that move, right? He's able to say, okay, now let's say there's some random flow, right? That only a certain number will deviate big, because that's how small the nucleus is, So that is a essential discovery of Rutherford. So part of learning all this is also to understand how these things are explained and understood. Okay, so after the so the other idea is that there is this idea of the stability of an atom, right? See, we rarely see, once things have stabilized, we rarely see any metamorphosis of atoms. There's not suddenly give a neutron, give a neutron, take a neutron, give a proton, take a proton, right? There, it never happens. There is give an electron, take an electron, but there is never give a proton, take a proton, right? Except for these special substances which we call as radioactive substances. If you look at your iron or all the normal things that we have in our world, you don't see any variation or morphing of these particles, right? And so and it's all very good, because if things were radioactive, we'll all get cancer. Okay, so the let's now look at the structure of the atom. Okay, so when we look at atoms, right, there was a later idea which revolved around the what we call as what Planck said, waves. Light was is essentially a wave. We don't so much talk about the weight of a light, right? It travels at a fixed velocity, which is c, right? All these electromagnetic waves travel at a fixed velocity, which is c, right? And all light particles have or light waves have a particular wavelength, and corresponding to that wavelength, a particular frequency, right? We all know this VIBGYOR, right? Violet, indigo, blue, green, yellow, orange, red, right? And they reflect a set of wavelengths. On this side of the V, you have what are called ultraviolet waves, which we can't see. On this side of the red, we have infrared waves, which also we can't see. Okay, so the ultraviolet and infrared we can't see. What we can see is limited to VIBGYOR. Okay, now if you scatter um, a light particle, right, from the sun, we see this VIBGYOR, right? Now, that is because the sun produces has a distinct set of a distinct type of light which contains a distinct set of frequencies. Okay? So those frequencies, if you, it does the um, water vapor, right, water droplets, they do also scatter infrared and ultraviolet possibly. Okay, it's just that we don't see it. Okay, but then it scatters it. You see these the separation of these frequencies, because each of them will have a different diffraction. Okay, and so that's what we end up seeing as so now E, the energy of a light wave equals h mu, where h is the Planck's constant. So h times mu is the energy, and mu equals c over lambda. C is the speed of light, 3 into 10 to the power of 8 meters per second, right? So now the so h mu, right? And we also know that the energy is equal to p square over 2m, right? How is that? E is equal to half mv square. Half mv square is what? And a p is what? Mv. So therefore, you have p square over 2m, right? And so, so from that, you can then derive an equation for, and for, with respect to the, um, you can then relate these terms, right? P equals mv, right? So from that, from p square by 2m, you can then derive additional values. Okay, if you need to find what is the energy from the momentum, etc. Right. So now Einstein's theory uh, is basically says that E is equal to mc square. Right. Now E is equal to mc square basically reflects the internal the equivalence of energy and matter. Okay, equivalence of energy and matter is given by that. So if something is traveling at is when you look at it, from light alone has a fixed, always has this velocity of 3 into 10 to the power of 8, right? Other things, when you look at the relative velocity, regardless of if you are moving vis-a-vis light, you still see 3 into 10 to the power of 8. Okay, but for other things you have this the associated velocity given by this, and the associated energy given by that, given by 1 by v square minus c square. Okay, so so the velocity equals f lambda or mu lambda, right? We already know that. Now the velocity is equal to e by t. Okay, and so from that you can see that you can write it as p square over e. Okay, p square over e is also given by v. Okay, so those manipulations you can easily do once you know e is equal to h mu, e is equal to half mv square. From all those things you can then do those manipulations. Now waves and particles. So um, waves and particles are, you know eventually they came up with this theory that a lot of matter is both a wave and a particle. A lot of these, particularly in the case of these subatomic particles, you can view them as both a wave or as a particle. And in very many theories they said yes, yes, this is our the right model. And we already looked at the Thompson model. We already looked at, Rutherford's model, right? Rutherford, basically, his main contribution came from this Rutherford's experiment with that gold foil, right? So he came up with, he had this gold foil, and then he accelerated this he had a lead box inside which he had a radioactive element, and he accelerated these alpha particles towards this, towards the screen. And he had this gold foil in the middle, and he very carefully calculated how much bending there was seen in these particles. Now Rutherford's model, as we already discussed last time, right? So its main drawback was, why weren't these electrons, you know going and banging into the nucleus and then getting destroyed, right? Or disappearing into the nucleus, right? Why would they keep stay outside and keep revolving outside, right? He couldn't explain the stability of the nucleus nor the line spectra. What keeps it all in place, right? Now, he had this very thin gold foil, and then he used alpha particles, okay, and they came from bismuth. Okay, and on the other side, he had a zinc sulfide screen, and then he had used microscopes to look at uh, you know um, what happened, right? Now most of the electrons are unscattered, they just pass through undeflected, right? But uh, the atom itself, he came up with this theory that an atom is only of a few angstroms in size. Okay, the size of an atom is in the few angstroms, right? Now the nucleus is 10 to the power of minus 15, and angstrom is 10 to the power of minus 10. So the nucleus was very, very small and very, very concentrated, you know. So the different so based on the recoil angle, right? When he used gold versus when he used a different material. See, he used gold, he used phosphorus, and he used boron, right? Now, boron, which by this time when this Mendeleev's periodic table had already been made, right? Boron, as you know, is uh, hydrogen, helium, lithium, beryllium, boron, right? So it's like, and then at a higher level you have phosphorus, and then a lot of with a lot of higher, much further along the in the periodic table you have gold, right? So he drew these curves which kind of indicated how much the deviation was, and based on that, the max deviations, right, he was then able to predict the recoil angles, right? The recoil angles where eventually some of the recoil angles will go to zero, right? But the biggest recoil angles he found was highest for gold, okay, and the lowest for beryllium. So he was able to say that these atoms were a little bit smaller and they had fewer, more importantly, fewer protons, right? Which verifies what we do. So it's concentrated and it's in the center. Okay, and so the and all the protons were together in the nucleus. Okay, and then therefore he was able to predict that. Now, the what they could not predict. So essentially the deviation of the alpha particle to the deviation of the electron, was of the order of 10 to the power of minus 4. Okay, so the electron would go faster, right? Because in the face of the nucleus, right? So what he said was all scattering is not due to the electrons at all. It's completely due to the positively charged nucleus. Okay, and that the radius, uh, you know um, was of the radius of the atom, right, was roughly 10 to the power of minus 10. So few angstroms. 10 to the power of minus 10 is a 1 angstrom, right? So roughly a few angstroms of the atom itself. But the nucleus was much smaller inside. The minimum radius was approximately 10 to the power of minus 14. Okay, so this was Rutherford's experiment. Okay, and as time evolved, Rutherford's scattering experiment became a centerpiece of the of the idea that the neutrons and the protons were at the center and the electrons revolved around them. But then, as we discussed, he could not explain why the atom was so stable and why the electrons didn't go and crash. Neither do the planets, right? But there is that possibility. But that never happens because so many things go and crash into the sun, right? You have so many of these what do you say, asteroids that come and hit the earth. There are so many that color all these other planets which don't have atmospheres, right? So what could explain this idea of and so basically he was able to say that because of the varying recoil angles, he was able to say that these had more charge, positive charges all in one place. There was not like little bits. Like plum pudding model was completely destroyed after Rutherford's experiment. A large fraction of alpha particles just went through. Positive charge is not uniformly distributed over any space, but concentrated in a very small part of the atom called the nucleus. So if there's anybody who discovered the nucleus, it is Rutherford. Okay, atoms are is electrically neutral. So he said that the electrons are revolving around. Okay, that what he could not explain was the stability. So Maxwell's theory, uh, you know, EM radiations emitted by the electrons will cause the orbit to decrease. So if there is an EM radiation, it goes to a lower orbit. When an atom emits an EM radiation, goes to a lower orbit, the question was, why was it able to still survive and stay in that lower orbit? Okay. And so for that, they came up with a new idea, which was eventually called the Bohr model, right? So, and these spectra, they weren't part of some continuum. They were very discrete. So it would go from this, when it went from this orbit to this orbit, it would lose exactly this much energy, and that energy would lead to a electromagnetic radiation being emitted. Okay, so that the energy lost by the electron became the corresponding electromagnetic radiation that was emitted. And they found they had all these so-called Lyman series, Balmer series, Passion series, etc. Which reflected the what we now know as the quantization of shells and the movement of electrons from one shell to another shell. Okay, so with that, I'm going to stop for today. And so we will pick up our discussion next time from Bohr model. Okay, next time when we start, we will discuss how Bohr overcame the issues of the Rutherford model, which said that why doesn't the electron go off into the nucleus, right? Why doesn't that happen? Rutherford explained that using what was an emerging field, which had been created by de Broglie and Planck, and all of them. They were working on this alternate science, alternate part of physics, which was called the quantum theory. So he then married the atomic model with the quantum theory, and of course, he was a very young man. Niels Bohr was a very young man, and he went and worked with Rutherford, and then he found all these ideas, and then using that, he was able to then marry the two theories, and he built this new Bohr model, which very well explained things. And to this day, Bohr's model is taught as the right model to students across the world in high school. Okay, so we will discuss the Bohr model next time. So with that, I'm going to stop for today. So have a great week.